Okay, thanks a lot for the invitation. It's kind of amazing that like it has been 12 years ago since I first talked in the scientific meeting. I think Ronald de Wolf was then one of the organizers. And since then, because I've been group leader for a while, I often got questions, is there a student in your group who can talk? And but now I just thought, okay, it's easier to just say, okay, I am happy to talk myself. And the reason is that like this question has been bugging me for a long time. Why are blackouts in power grids heavy-tailed? It has been one of the key questions in my Vici grant, which was about heavy-tailed distributions. And so this was one of the questions that really was bugging me. And somehow last year I've been telling everybody who did want to hear it and also who did not want to hear it. But it is probably one of the last times I'm going to give a talk about it. So this is joint work with Tommaso Nesti and Fiona Sloothaak. Tommaso was a PhD student at CWI. He's now waiting for his O1 visa application to go through so as to be able to work in Silicon Valley. H1s are not working out this year, hopefully after November again soon. And Fiona Sloothaak was another PhD student of mine. She was located at Eindhoven University of Technology, co-advised with Sam Borst. And she's currently a postdoc with Geert-Jan van Houtem in the Industrial Engineering Department at TUI. And it was a very nice collaboration. They were both in their final year, and Fiona was looking at macroscopic models for blackouts, and Tommaso at microscopic models. And we try to, like all the things they learned in the first 3 years, try to combine everything. And that was kind of the goal. And I think, well, I'll leave it up to you, but I was quite happy about how this collaboration turned out. All right, so I'm going to talk a little bit about blackouts and heavy tails first. Then I'll go on to the main point of this talk. And then I will give you some modeling and analysis and a case study, and also some conclusion and plans for the future. Okay, so yeah, this is not, I mean, this is a fake picture. It's not very good for a scientific presentation, but at least I am honest. There are NASA satellite images that are not as clear as this one. The point of the slide that I want to make is that on August 11, 2003, there was a blackout in the US. And what happened, it took a long time before they figured out what happened, but what truly happened was that there was a software error. Because of the software error, there was that was like one cause. A second cause was that a line, a power line was overheated. If our power line overheats, it sags, so it's going down, and it hit a tree. But because of the software error, they thought something else happened, and because of that, they started making all the wrong precautionary measures. And because of that, more outages occurred. And because of that, all the energy that was normally going from the Chicago to the New York area had to go through the other side of the Great Lakes. And then everything broke down as a result. And 55 million people had no power for up to 4 days. It took 4 days to resolve this. And so this was a big blackout, but in general, there are also like smaller blackouts, and it's quite costly. And more recently, people started to worry about maybe renewable energy having maybe causing even more blackouts. So there was kind of like questions like, can we understand these blackouts? A generic question. So this is a slide from DNV-GL. And that shows its color. It's a color. It's so nice slide. I could never have made this myself. So it's like color coded. The colors refer to continents, and then the size of the ball, obviously, how many people got into trouble. So this is India has the world record, 600 million people without blackouts. Blackouts happen quite frequently in India. This goes up to 2015. We had one. That was a funny one. Well, funny for CWI. There was a blackout because there was a problem in Diemen. There was like not a line failure, but there was a node failure, let's say. It took them several hours to figure out which part of the station in Diemen had a problem. But during that, the UvA on the other side of the street of Science Park had no power, while CWI had power. And that was kind of a funny detail. There are other, I mean, I can talk anecdotes for half an hour based on this slide. So let me just tell you one more. Here's the geomagnetic storm. This is where some other people at CWI work on the space weather and so on. There is one here, another one, a really fine one. This was a ship that had to go through a canal in Germany, and the ship had to pass a big power line, but the ship was an hour earlier, so called the German network operator to ask, can you switch off the power line now because I'm earlier? And then the German network operator says, fine, I'll switch it off. But meanwhile, it was very windy in Poland, and the French bought Polish wind energy. So Germany, all the cables in Germany had to be used to transfer. So they lost capacity. And so the entire European grid got split into 3 pieces. And there were also some Dutch villages involved. So there are like all kinds of anecdotes. I mean, they're not nice blackouts. People can die as a result, and but there are all kinds of anecdotes, and so like what can we do with a bunch of anecdotes? So that was kind of like one of the questions. So actually, there was a power outage in Schiphol where TNO had to come up with a preliminary reason on why this occurred, and that still took 5 months. The TenneT, I'm not sure if it has been concluded or not, but the official one, the careful one of TenneT, goes quicker. There was in last year in the UK, there was also an outage. There was an interesting outage because at the same time a classical generator failed, and there was also a problem with the wind park. It was kind of like a hybrid thing of like a renewable energy problem and classical problem. And so like all kinds of things can go wrong, and from a complex systems point of view, the question is, can you find something simple, some emergent behavior, and so I co-organized a special semester on power grids at the Newton Institute last year, and I wanted to have a track on blackouts, and so I tried to get support in the international community, and I got mixed reports. And some of the people, these were some of the feedback that I got. Because it's not a complex system, but it's a complicated system in the sense that like every time there is some kind of ridiculous chain of events that nobody can even think of while writing a movie script that happened, and then it takes 2 years to find out, and then you say, okay, this happened. And somebody else said like it's not possible to come up with about interesting and useful results. So and I had like during that semester more discussion. So like a power system is like a very high dimensional nonlinear differential equation, and so this could really be a case where it may be better to use simple black box models to kind of try to predict anomalies using machine learning techniques rather than using very sophisticated high dimensional mathematical models. That can all be true, but I am kind of stubborn. And honestly, also tenure. So I was like, okay, I don't care what you say, we're gonna try. I didn't tell all this to my PhD students, of course. They were blissfully ignorant. And I knew, to be honest, I was not that cruel to my students. I knew that one feature of blackouts is not complicated at all. And that is the statistical distribution of blackout sizes in power grids. So if you look at how much power could not be delivered to consumers in terms of megawatts, or you look at how many households were affected during the blackout, and so these are data from the US. So the US is very transparent about their blackout, contrary to European countries where it's very hard to find. But like whenever there is a failure in the US that affects at least 15,000 customers, they document it and they put it in an Excel file which you can download. So it is like a data set of over 2,000 failures from the last 35 years, and that's very nice. So what is happening here is like you take the empirical distribution and you put it on a log plot and you get a straight line. yeah, then so that suggests that there is a power law, and like you can do that with all kinds of distributions, and often it's kind of overprescribed. But here, if you do statistical tests, it's really significant a power law. So the question is, okay, so power laws are important because it means that it's not a Gaussian distribution. So it means that like big blackouts happen more often than you would expect based on Gaussian distribution. So even the big blackouts happen more frequently than you want, let's say. And as a result, you have to do something about it. And if you want to do something about it, you have to understand why these blackouts occur. And that kind of was driving us. So I need to say something about Pareto distributions versus Gaussian distributions. So a Pareto distribution is a heavy-tailed distribution where extreme values are relatively frequent. And so Pareto was an economist that studied incomes. And so for wealth, it's typically you have the standard joke, if Bill Gates walks into a bar, everybody is a millionaire on average. And so even there was the debate between the vice presidents where Mike Pence also said, like, the American households got a $4,000 tax cut on average, but like the median tax cut was probably epsilon. But so like averages like when it comes to money, averages are pretty much meaningless. And there are like other examples where an average is not such an informative thing, and blackout is one of them. Contrary to, for example, length of the human body. If you are in a bar and the average length of a human in the bar is 2 meters, it's quite likely that the basketball team is having a party. There must be some kind of cause why everybody is long, and there is not one person of 10 meters tall and the others are average. So it's kind of like totally different types of intuition. So the heavy tails, like light tails, have been studied since the 19th century, starting in rare event concept with Boltzmann, and later in insurance also Kramer. And heavy tails is much more frequent. And like the question is, why do the rare events occur? So here is a conspiracy. Like the basketball team was sent into the bar, everybody is a little longer than you would expect. And with the money, it's just like one really rich person and the rest has average wealth. Okay, so so there are like, these are the 3 canonical examples of heavy tails. So we'll be looking at the Pareto tails, but you can also think of log normal tails and Weibull tails. And there are key properties here. First of all, you don't have moment generating functions. So like convex duality techniques are hard to apply in the analysis, contrary to light tail distributions. And then there is an intuitively appealing property that you should remember at least for 10 more minutes, which is that the probability that the sum of heavy-tailed random variables is large is roughly equivalent to the probability that the maximum is large. This is this Bill Gates walks into a bar type of principle. Okay. Good. So heavy tails, as I said, are everywhere. And so actually, when I was a PhD student, I was at CWY, PhD student of Onno Boxma. And at that point, this was late 90s. At that point, they started to collect data of file sizes. And it turned out that file sizes are heavy-tailed. And also delays on the internet and so on, at least then probably still are heavy-tailed. And so we started studying queuing systems with heavy-tailed service times. And you see there in queuing systems, queuing networks, if service times are heavy-tailed, also queue lengths and waiting times are heavy-tailed. So this is really an example, like you're primarily interested in waiting times. The waiting times were heavy-tailed because the input of the model is heavy-tailed. So the dynamics of the model does not really cause the heavy-tailed behavior. It's the input to the model, which were the heavy-tailed service times or heavy-tailed file sizes that cause heavy-tailed output. So in finance, you have the old models, like Black and Scholes type of models that have like Gaussian tails that were used up to 1987 when there was a big crash. And Nassim Taleb made a lot of money there and he became famous after that. And so in finance, like losses happen more frequently than you would expect based on Black-Scholes type of models. And the reason is that yeah, there are all kinds of nonlinear phenomena going on in these models. So there is a phenomenon called stochastic volatility. It basically means that if there is a lot of unrest in the market today, there is very likely also a lot of unrest in the market tomorrow. And like this compounding unrest can lead to subsequent losses over several days. And that makes it easier to lose a lot of money. So in social networks, there is another type of model that causes heavy tail, so which is called preferential attachment. So there's the preferential attachment mechanism that basically says that if you increase the size of a network, you add a node to the network, like a new node is typically linked to nodes that already have a lot of links. So you have the rich get richer phenomenon, but then in a network context. And that is also like you see that also with scientists in like number of collaborations. Of course, you see it also with grants. People who already got a lot of money will get even more, and then so on. And then there is the fourth one, and which is the unknown. I mean, it was unknown at least. So what happens with energy systems? That is the question. And so I pretty much summarized almost what is on this slide. And then there is the fourth one. This is this enigmatic thing that the physicists love, which is called self-organized criticality or criticality, which basically means that, like, so the most simple example is a branching process where the offspring distribution, the mean offspring is equal to 1. So this branching process will die out eventually, but the total size of the tree that it generates has a heavy tail, it has a power law. And it actually has a heavy tail with infinite mean. And so existing work on blackouts, and so like this is criticality, but then there's self-organized version of criticality, which basically the narrative here is that because a power system is supposed in a cost-efficient way, it is behaving as if it is as if it is a critical system. And so it's a self-organized way. And so in the engineering literature, the intuition the engineers have is that you have a power system and then a bunch of failures occur. And then after a couple of years, you need to decide where to do the network upgrades. And you tend to do the network upgrades at that part of the network where there has been a lot of failures. And if you do that, and so they model that, and they basically, they have these very big models, and they simulate that, and then they compare certain simulation traces with traces of a sandpile model, and they say, well, both of them have long-range dependence, so it must be the same mechanism. But what they don't have any mathematical results, and they basically have an intuition and a narrative. They don't really show from a physical model like an emergent behavior within the same model, not even through simulations. They just say there is an analogy. And so to me, as a mathematician, it was kind of not very convincing. And but I also thought it should be due to some critical phenomena. I thought this, and we try to somehow make this rigorous and do a lot of simulation. So the good thing was that Tommaso was very good in setting up all these big simulations, but we couldn't get from these models critical phenomena. And then actually in the spring of 2018, I was not physically very fit, and it was like the flu season was pretty hectic in 2018, and I got pneumonia. It was, I mean, this is pretty bad in itself. I am asthmatic, so I was in bed for 5-6 weeks. I got extremely bored, of course, and then I actually got onto the Wikipedia of German city sizes, and then the lightning struck basically, because like Berlin is twice as big as Hamburg, 3 times as big as Munich, 4 times as big as Cologne, 5 times as big as Frankfurt. And we were doing another study on some cascading modeling, more like a microscopic model, where we actually had Germany. We had like a very nice detailed model of Germany where we're doing experiments with. So I was associating Germany already with blackouts. And because I saw this, I was able to associate it, because this is called zip law. It's city sizes that they have a power law is already known since 1906. I mean, I didn't know it back then, but we did some literature search. So city size in many countries have a power law. In many of the developed countries, some African countries, it's not the case, but in most of the developed countries, they have a power law. And so then, yeah, we did the data analysis, and then the confidence intervals for the index of the power law really overlap to a large extent. And so that's okay. So the city sizes have to do something with this. That was like the hypothesis. And so so here, this is a little bit more data analysis. This is called the hill plot, where you blue are city sizes and orange are blackout sizes. So what is the hill plot? So typically Pareto or power law, you don't see it in the entire distribution. You only see it for the big values. So what you do is you choose a cutoff point, x min, and then based on the values that exceed x min, you fit a power law. And so the idea is that if x min is very large, you don't have a lot of data, so you'll get a lot of noise because you don't have a lot of data. But if x min is really small, you get a bias because you don't have a power law in the entire distribution. But then there is this sweet spot in the middle where it should be stable. That's kind of like the idea, and you can formalize this in more mathematical tests. But like if you do the exploratory data analysis, then you get this type of pictures. And so you need to choose a cutoff. So there is a paper of Clauset et al., the PL fit method that suggests then how to choose the cutoff. So here you get it for the city size, here for the blackout sizes. So now the funny anecdote I have to say is that in the 90s, when electrical engineers first started fit Pareto tail, they did it in a let's say friendly way, suboptimal way. They used all data points, not just the largest one, but all data points. So because of that, they ended up here, and they ended up with model. They say, okay, this has an infinite mean, because like an index of less than 1 suggests infinite mean. And this is what drove them, I think, to the branching process. Although I talked to the co-authors, and they cannot recall this at this point, and they don't believe that city sizes yet have something to do with it. We have ongoing debates now. But yeah, but yeah, like it really depends. Like if you have these power laws, like at least you have to do a cutoff, otherwise you don't get a reliable fit. So, of course, like this is some association that I make, and then the question is, why is this relevant? So this is my intuition. Initially, the network is fully connected in such a way that supply is equal to demand. This is how power grids operate. Then a failure occurs, and I'm almost out of time. So I don't have time to say the model. That's good. But so then after the intuition, I'll stop.
Talk for at least 6 more minutes, I think.
I see. So so because of a failure occurs, the law of physics prescribes how the energy will flow on the remaining network. But then because of that, other lines will get more heavily loaded. That leads to other failures, and that's called, like, the sequence of failures is called a cascade. Now at some point, so many failures will have occurred that the network is no longer connected. So you have, let's say, 2 subnetworks where, because the original network was supply equal to demand, at least one of those subnetworks will have a shortage. Now, if you look at the demand in this subnetwork, you can write this as the sum of the demands from all the cities. Now, assume that the demand is proportional to the population. You see that the demand in each subnetwork is heavy-tailed. And since city sizes, are heavy-tailed, you will have in that subnetwork that a heavy-tailed number of consumers will have a problem. Now the key question now is, like, is the mismatch between supply and demand also heavy-tailed? And for that, what you need is that a cascade needs to produce a cut of the network that leads to a heavy-tailed mismatch. Now the question philosophically is this even possible? Because cables, there are only 12 different types of cables depending on the voltage, but like sometimes they have like more lines from A to B, and this is an abstraction. At least impedance data show that the impedance, which is the relevant metric here, is heavy-tailed. So we have a model that actually rigorously shows that this mismatch is heavy-tailed. And I don't have a lot of time to go through the model. So the model is a random graph, but the topology of the network is not random. We assume a fixed topology. but we assume that the city sizes are random and they are drawn from a Pareto distribution. And based on the city sizes, we have to decide what is the capacity of the lines. So the lines are fixed. We just have to determine the capacity, and they will depend on city sizes. And so this is done. The capacity lines are set in a planning model. Then based on capacities, we are determining, we have an operational model to determine how actually the power flows go, and then we do the cascade in the emergency. So in the operational stage, what we solve is so-called the DC OPF. This is the standard operational problem that is being solved every half hour to determine what should be the production scheme of all the generators. And these line limits here appear, and we set those line limits in a planning problem, these F bars, by simply solving this optimization problem without this constraint. So we solve it without this constraint, then you just get an average as an explicit solution for the GIs. So GIs are how much power every node produces. And so you get this explicit expression, and that gives these line limits. So we let lambda be a safety parameter that basically says, okay, this is how the percentage we want to stay away from the line limits. And we use that in the operational stage. I'm sorry that I'm going so fast. I think spending a few more minutes would also not help. So we have this model that gives you these line limits. So this is and the nice thing, so this leads to these line flows. They depend on the city sizes. So we view them as random variables. This is kind of like a modeling trick. And then we start running a cascade. So the nice thing now is that using heavy-tailed large deviations, the most dominant, so the main randomness is like the first line that trips and the city size. So we keep the city sizes random. So now the main event that will contribute to the rare event we care about, which is a large blackout size, is the event where there is one big cities and the remaining city sizes are small. And what we then do is a renormalization. We assume the big city is size 1 and all the small cities are size 0. For that scenario, we can solve the planning and the operational problem explicitly, and we can analyze the blackout explicitly. And then we have to show that this renormalization argument is mathematically rigorous. We need to prove a certain stability result, saying that if you move away from this configuration, then the blackout sequence is the same. And this is this was extremely difficult. That took us 6 more months to really prove that. If we would have just not done it, then we would have had a slightly weaker result. So now in our model, we really have like not only a power law for a blackout size, but also a pre-constant. And without that extra 6 months, we would have had a lim inf and a lim sub, which were positive and finite. But as a mathematician, we kind of, got a little bit overboard with that. Okay. So that's kind of like the idea. And so I've sent links to the paper. The paper appeared in PRL. But there is a link, there is on the archive, the full version with the 20-page appendix if you really care about the proofs. All right. So we did some numerical studies because like referees and also engineers are very skeptical. So first of all, if you look at like one city typically is connected through the network with several nodes. And there are all kinds of other constraints. The physics is not linear, but it's non-linear. And so on. And so we did all kinds of tests that showed that at least from a numerical standpoint, the result is pretty robust. And so in particular, if we replace the heavy-tailed city sizes with light-tailed city sizes, we don't get heavy-tailed blackout sizes. So the critical assumption of the model is the fact that in practice, the city sizes are frozen. while our city sizes, we took them random. And so like what in our model, basically a power, like a blackout, generating a blackout is basically a way of bootstrapping city sizes. So if your data set is like 2,000 blackout data compared to the North American grid, which has like 100,000 nodes, then the bootstrap sample is small compared to the size of the network, and like theory, bootstrap theory suggests then you should still see it in the data. So that's kind of consistent. And so we went on a big computer. At some point at the groepsleidersoverleg, I asked people to can I borrow some cluster time? But in the end, we were able to use a big computer, and we did and we showed like if you have 10,000 nodes, then a network of 10,000 nodes, then you start seeing it despite that the city size are frozen. So we also, for the German network, you don't see that. Like a blackout, like if a big blackout occurs, it's very simple. Either the Ruhr area has a problem, or Berlin has a problem, or Hamburg has a problem, or Munich has a problem. That's it. But this heuristic from heavy-tailed, like the catastrophe principle, that you only have a big jump, we do see that phenomenon. So we don't get statistically significant Pareto tails for the German model, but we do get this big jump. The phenomenon still persists, even though you don't have a power law. So I think that's a good time to end. And and so one question is that, like, there are many. So like in complex network theory, that's the thing I'm pretty excited about that as a mathematician. We know from complex network is like most virtual networks have a network topology that has that is scale free, has the nodes, the degree of the nodes have a power law, but most physical networks don't. And so in particular, transport networks, train networks, they don't have this. But then like, are the city sizes relevant? So we found a paper from the computer science literature where a certain transportation planning heuristic, which is MP complete, some heuristic performed remarkably well, and they also think that it is because of the city sizes. So with Nikhil, we started to think about whether we can make this rigorous using this type of modeling, but then the corona started, and we didn't start yet. But this is one of my next plans, and I should stop here. Thank you for your attention.
Thank you, Bert, for this great talk. We're a little short on time, but maybe if people have questions, I think we can either take a short question now via the chat, or we can do it maybe after Laura's talk at the end. So let's see, are there questions in the chat? I think not yet. Maybe I have, okay, I can ask a short question. Basically, knowing this, what would you advise to build sort of a more resilient power grid if you could redesign a country?
Actually, that's a good that you say that. I forgot to say it. So when you go back to the causes, what causes the heavy-tailed? It's the input. And the city sizes are heavy-tailed since 1906, and they're going to stay that. So no matter what network you design, you will always have this problem. And so I write that also here. It makes more sense to focus on the capability for a city to survive a blackout of a given duration. So like make cities more resilient so that you can survive a blackout of, for example, 12 hours. Because if you look at the data of the duration of blackout sizes, that goes down much quicker. And so I think, I'm not saying that we should spend zero money on network upgrades. Like network upgrades are important for typical scenarios, but like for the very rare events, there's no network upgrade that will save you. It will always go wrong at some point.
Okay, so we should keep some cash at home for when the digital.
No, I think we should have batteries at home.
Yeah.
To survive a blackout. That's what I think. That's what I mean. I don't have it myself, so I don't practice what I preach here. But I think we should have a battery. But we will get batteries because of the electric cars. It will be bi-directional, and the electric cars maybe will save us.
Okay. Yeah, I was just about to ask if that's also a bit of a question of kind of localized versus centralized supply.
Yeah, so this problem can only be solved by going more local, in my opinion.